Welcome to Unit 4. We have explored atomic structure, dove deep into what is in the nucleus and how to calculate mass. And so this unit we're going to move our way out and talk about electrons and exactly what is the electron cloud, where exactly are those electrons located, in an effort to better understand reactivity. So we're also going to touch upon some chemical reactions in this unit and how they're represented and how they model. So the essential question for this topic area, elements in the periodic table, is I want you to think about where exactly are the electrons located in the electron cloud. In other words, if we were to write them an address, what would that look like? We're going to start small. We're really just going to talk about the distance away from the nucleus in this PowerPoint. We'll get into a more specific location as best as we can in subsequent units. So one concept you first have to understand are energy levels. Electrons aren't in specific locations because they are constantly moving, but they are in a general area. So we can kind of say roughly where they're located, but we can't give them an exact X, Y, and Z location. So energy levels are how far away those general areas are from the nucleus. And we refer to those energy levels primarily as main energy levels, but there can also be sub-energy levels. But each main energy level consists of these clouds, and they're clouds because it's an accumulation of a lot of different snapshots of electron movement over time. But each energy level consists of a cloud of electron density. Within each of those energy levels or shells, there's also going to be smaller areas called orbitals. We're not going to talk about orbitals today. We're going to save that for Unit 5. So Bohr was a scientist that did a lot of experimentation and studies of electrons in order to try to pinpoint their location to help better explain reactivity. And he came up with a theory that has four points to it that I want you to be aware of. He said that electrons, because they are constantly moving, they're moving, almost orbiting around the nucleus in fixed circular paths called energy levels or shells. You may hear it either way. We know that this is not completely accurate because there are sublevels and orbitals that don't make the shape of a circular path. But for this unit, we're going to start with the oldest theory. Those energy levels are primarily represented by numbers, but you may see in old literature that they're represented by the letters K, L, M, and O, P. The circular path closest to the nucleus is the first energy level, and then it goes up in number the further you get away from the nucleus. As long as the electrons stay within their distance away from the nucleus, so as long as they stay on their energy levels, the energy they possess will not change. They'll just keep moving at the same speed with the same amount of energy. However, if you hit that atom with a certain amount of energy, quantum amount of energy, the electrons can absorb the energy and jump up to a higher energy level, in which case they are unstable and they quickly fall back down and emit the energy that they had absorbed as visible light. So let's take a look at what this model looks like. Almost looks like a bullseye. So that black center is that dense nucleus that Rutherford had found that we talked about last unit. That's where all the protons and the neutrons are. And then those circles that you see emanating from that center represent energy levels where we could possibly find electrons. Notice that that first energy level, that first red circle, is very small. If it's very small, you're not going to have that many electrons on it. And they get bigger and bigger and bigger as you go out. So the farther away you are from the nucleus, the larger your radius. The electrons are going to be possess more energy, and you can fit more electrons on them. So let's say I've got an electron on that first energy level. If you hit that atom with a certain amount of energy, the exact difference between the first and the second energy level, an electron can absorb or take all that energy and jump up to another energy level. But it leaves an open seat on that first energy level, so it's an unstable situation, and that electron will quickly fall back down to the first energy level and emit light that we see. So Bohr's model gave us the first part of our electron configurations. Bohr's model gave us how to identify those principal energy levels. In other words, how far are the electrons from the nucleus? And those principal energy levels is one of 4 quantum numbers. We refer to those energy levels as the principal quantum number. It tells us how much energy or how far away those electrons are from the nucleus. And you saw those circles. Not every energy level is going to be able to have the same amount of electrons. So I want you to take out and look at your periodic table for the moment. Our periodic table has different rows. We call those rows our periods. Each period represents a new energy level. Okay? We don't have half energy levels. Every time you go down a row, you are in a new energy level. So we only have whole numbers for our principal quantum number. The larger the principal quantum number, the farther those electrons are from the nucleus, and the more energy they possess. So if you look at that first row on your periodic table, you only see 2 elements. Most of hydrogen will only have, neutral hydrogen will only have 1 electron. Helium, neutral atom of helium, is going to have 2 electrons. So the max capacity on that first energy level is only 2 electrons. Come down to the second row, and if you count across that second row, you'll see 8 elements. So the max capacity for the second energy level is 8. This is where things get interesting. If you look at that third energy level and you count across, you only see 8, but the max capacity for that third energy level is 18. Those other 10 are those first that first transition group, starting with scandium and going to zinc. Those electrons are actually on the third energy level. And we'll get into more of why they sit there on the periodic table next unit. But the third has a max capacity of 18. The fourth has a max capacity of 32. And those include the lanthanoid series and the actinoid series. So let's take a look at what a Bohr's model would look like for a particular element. I want to take a look at a neutral sodium atom. Neutral means that the number of protons will equal the number of electrons. So let's find sodium on the periodic table. It has an atomic number of 11, which means it has 11 protons, should have 11 electrons. It is that in that first column on that third row or third period. So I have to place 11 electrons around that nucleus. Remember, that first energy level can only have 2. So after I put 2 electrons separated from one another on that first energy level, I'm done. I can't put any more on there. The second energy level can only hold 8. So I'm going to put 8 on that second circle, radiating out. And once I put 8, I am done. I have placed a total of 10 electrons. So the last remaining electron is going to go on that last circle, the farthest from the nucleus. We call that the outer shell or the valence shell. So here's an example for a sodium atom. You'll find this as number 2 on page 6. Go ahead and pause and try to draw the Bohr's model for magnesium, neon, argon, aluminum, and oxygen. And then return back here and we'll go into valence electrons a little bit further. So looking at the periodic table is going to give us a lot of information about not just the mass and the number of protons and whether or not it's a metal or a non-metal, but it's also going to tell us something about the valence electrons as well. Your valence electrons are the ones located on the very last energy level, or the circle the farthest away from the nucleus. There is a repeating, or what we refer to as a periodic pattern, that we can use the periodic table for in regards to valence electrons. As you start in that first column and go across to the 18th column, your valence electrons are going to increase in number. Okay, so, but it will drop back down and start over again. That's what we mean by repeating or periodic, when you go up an energy level or you go down to a new row. Here's a look at how we determine the number of valence electrons for each element. Every element in that first column has 1 valence electron. Everything in group 2 has 2. Notice we're going to skip over the transition metals. Okay, technically, all those transition metals also only have 2 valence electrons, but they've got some other electrons that can act like valence electrons. So we're going to hold off on talking about our transition metals until next unit. Group 13, this is where it gets a little tricky, is going to have 3, not 13. If you go across, the maximum amount of valence electrons any element can have is 8. So from 13 to 18, it goes 3, 4, 5, 6, 7, 8. Except for helium, because helium can only have 2 electrons. It only has 2 protons. It's going to have 2 electrons. So that is how we can use our periodic table to determine the number of valence electrons. So coming back to that neutral sodium atom that we talked about earlier when we were practicing Bohr's model, there's that arrow pointing to that 1 valence electron. So if I were to look at potassium, it's going to be very similar, but it's going to have 1 more circle, so it's going to be a little bit bigger than the sodium, but it's only going to have 1 electron on there. So that is the location of the valence electrons. Now let's go ahead and practice and see if we can check our understanding of valence electrons. So let's check our knowledge. I would ask you to pause for a second, find these elements on the periodic table, and see how many valence electrons you have. So here are the answers to those valence electrons. Hopefully you did okay. For further practice, please complete pages 8 and 10 in your packet to gain a better understanding. Your first daily quiz will be on drawing a Bohr's model for a particular element. So you do need to know or memorize the max capacity. Here's a hint, we're not going to do anything beyond the 3rd energy level or beyond argon. So as long as you have your periodic table in front of you, you'll know where to place those electrons. You also need to know or be able to identify the number of valence electrons if we give you an element. Find it on the periodic table, see which column it is in. Remember, you can only have a max of 8. And speaking of 8, the max capacity is 8, and we refer to that as the octet rule. Our next video will be going a little bit further on why those valence electrons are important when we talk about the creation of ions. Thank you.